Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. Let's get straight into the action here. We are going to look at special right triangles. And before I do, I want to make sure we know how to simplify square root radicals. This will be revisiting it. So if you haven't seen this before, it might be a little confusing. This is going for people who've kind of seen it before. Maybe you can pick up on it. So I'm not gonna linger on this much, even with the numerous examples that I have. After that, we'll look at these specific ones, the 45-45-90 right triangle and the 30-60-90 right triangle. And guys, these are special in a way that they have special ratio relationship. These exist in pre-calc and trig and calculus all the time, everywhere you see them. So adhere to them, please, when you look at them. And then some Pythagorean triples. It's just a nice little thing to do in case you can save yourself from using Pythagorean theorem when you don't have to. All right, let's go straight into the action, guys. Let's look at simplifying square root radicals. You can simplify the square root of a non-perfect square value by factoring out perfect squares from the value and then taking their square root. A radical is fully simplified once all perfect squares are factored from the original value. So we're going to use this property where if you can factor out some numbers, you can also split them apart inside, so that the square root of a product equals the product of two square roots. And we're going to use this in such a way, I'm probably not even going to write it this way. I'm just going to go kind of straight into that action. My goal in all these numbers here that have a square root, see, 96 is not a perfect square. I can't just take the square root and have it be an integer. But there exists, possibly, in all these there will be, there exist perfect square factors inside 96, such as I can divide 96 by 4. I can divide 96 by 16. What's special about numbers 4 and 16? I can take the square roots of those numbers. The square root of 4 is 2, the square root of 16 is 4. I think 16 is the largest perfect square I can pull out of here, so I'm going to go ahead and do that. Hey, 96 is 16 times 6. So the square root of 96 is the square root of 16 times the square root of 6. And you want to try and find the largest perfect square factor. Otherwise, you'll have to kind of do it again. You know what I mean? Because if there are still perfect square factors inside what remains, you got to pull it out again. The square root of 16 is 4, so this becomes 4 root 6. Again, guys, I'm not going to linger on this. The first one was the most I'm going to linger on these. The square root of 175, again, try and divide out perfect square factors. 4, no. Probably no even numbers, right? Because this is an odd number. 9, 9 doesn't work. 16, no. 25, 25 sounds good, right? Quarters, $1.75. If I split this up, even if it's not the largest one, at least I'm secured in it. I know that it will work. 25 and what is it, 7. So it is the largest one because 7 as a prime number definitely doesn't have any perfect square factors. The square root of 25 is 5. And I get 5 root 7. These are simplified versions of this stuff here. And finally, 7 times the square root of 600. Hey, when in doubt, guys, factor out 100 from there. Now, there's another fly in the ointment, guys. 7 is also outside of here. But the square root of 100 times the square root of 6. The square root of 100 is 10. So what do? Do I write 710? Well, I write 7 times 10, right? 7 root 600 means 7 times the square root of 600. So 7 times 10 root 6, and this becomes 70 root 6. So that's the basis behind simplifying these square root values right here. There's another portion of this that I need to do that's called rationalizing the denominator, and it's probably the one that maybe you guys don't know as much about, so let's jump to it. Okay, rationalizing the denominator means if you have an irrational value in the denominator, such as these ones right here, we have to make sure that the denominator has an integer value. That also includes, guys, no decimals in your denominators. Really no fractions within fractions. They also don't like negatives within there. I mean, there are a lot of things within denominators that, as far as simplifying goes, we want it to just be a whole, a positive whole. And that's especially true for these things right here. These are all irrational values. I can't simply just take the square root and then I'm done. I want to make sure there is no irrational, no square root in there whatsoever. So here's what you're going to do. To rationalize the denominator, we must multiply both the top and bottom of the fraction by the irrational denominator, the value that we see there, as to not change its actual value. And what this means here, when you have 4 over square root of 3, I want to multiply top and bottom of this thing by square root of 3. Now, the reason why I have to do top and bottom is because root 3 over root 3 is 1. When I multiply by 1, I'm not changing its value. right? It's like whenever you find a common denominator. Hey, multiply top and bottom, 5 over 5. We can't change the value. We're just going to change its appearance. Now, why am I choosing root 3 in and of itself? Because when I multiply a square root of some value by itself, the square root of some value, you just get the value that's in there. That means, guys, the square root of 3 times the square root of 3 is 3. I have rationalized my denominator. Now, the numerator, bears the burden of sometimes having something like 4 root 3. But this, guys, this becomes 4 root 3 over 3. Believe it or not, that is considered simplified. It might not look as clean as the original thing. Sometimes it will clean up, and this is a version that is not clean. The majority of these other ones will clean up in our favor. So let's take a look. How about we do this one times root 3 over 3? What's going to happen here? Or root 3 over root 3, I should say. On the bottom, once again, you get 3. On the top, you get 6 root 3. Am I done? Well, no, because I can do 6 divided by 3 right here, guys, and I get 2. And here I have the root 3. So I'm left with 2 root 3 as that answer there. That simplification actually kind of helped us. It favored us in some sort of way. And you might be wondering why I didn't divide 3 over 3 right here. Because this isn't 3, guys. It's the square root of 3. It's closer to 1.7 something. It's not a true 3, basically. But you can do these ones together. And you can mingle. Now, this one right here, guys, I'm just going to let you know that although I couldn't do root 3 divided by 3, you can actually turn these and merge these together. Just like how on this previous one, I split up these fractions. You can also merge them back together. This product. You can also do the same thing with fractions. I could have just done this. Root 6 divided by root 3 is, root 2 like that, and then I'm done. And this will be the answer we get. But just to practice rationalizing denominator, in case this is something you don't notice, let's look at this in a larger way. Times root 3 over root 3 here. And what I'm going to get, root 6 times root 3, once again, merging them, we're going to get root 18. And this is over 3. Now, hey, this isn't root 2, Mr. Robinson. I thought you said we get root 2. Root 18 can be simplified. Root 18, I can pull out a root 9 because 9 is a perfect square. So I can do root 9 times root 2 over 3, which is 3 root 2 over 3. I see it. 3 over 3 is 1, and you're left with the square root of 2. So you still get to the square root of 2 no matter what you do there. But if you notice, root 6 over root 3, I mean, that does become just root 2 just by dividing. You can divide radicals with radicals, perfect square roots with square roots. And you can divide integers with, rationals with rationals. But anyway, I might practice that a couple times anyway, and sometimes you kind of have to use it. All right, this one right here, I'm going to multiply top and bottom by root 8. I'll show you an alternative to this here, and it's kind of in my instruction. But here I get 4 root 8 over 8, and then 4 over 8 can reduce to 1/2, so I get root 8 over 2, 1 root 8 over 2, and square root of 8 can simplify to root 4 times root 2 over 2, which is 2 root 2 over 2, which, hey, I've seen this before. That is square root of 2. So there's one way. Now, you might want to pause this video, guys, because I'm going to do another version of this one, which means I need to erase all this right here. But I get square root of 2 right there, okay? Now, an alternative version of this, if you notice, guys, the square root of 8 that I had to simplify on top started on bottom. So what if I simplified the square root of 8 to begin with? So I turned this into 4 over root 4 root 2, which is 4 over 2 root 2. Well, this might be helpful for us, even though this isn't yet rationalized as a denominator. This cleans us up a lot more. 4 over 2, guys, becomes 2. So I have a 2 over top on the top, and then I have the root 2 on bottom. Now when I rationalize, I don't have to multiply both sides, the top and bottom, by a root 8. I can just do root 2 here. So root 2 over root 2. I don't know if this is faster in this problem here. But that becomes 2 root 2 over 2, which again, we do get the root 2. There are a lot of ways to do this. I just want to give you all the different strategies as long as I'm on this set. And last one here, root 5 over root 15. Same thing. Do I go straight to root 15 over root 15? After all, we can't simplify root 15, and that's true. We can't simplify root 15. So do I go straight to this? Well, maybe look to just like we did on this problem right here. Remember when we divided these outright? What if I reduce this fraction? Remember, this is root 5 over 15 like that. I can reduce this basically, right? I can divide the 5 and 15. I can change this into root 1 over root 3. And hey, the square root of 1 is 1. I can turn this into 1 over root 3, guys. That's fine. That's allowed. I can reduce this. It's not simplified yet, though, in the sense that I haven't rationalized the denominator. So I got to take my 1 root 3, and I got to multiply now by root 3 over root 3. And I will get root 3 over 3. And that is the simplified version. So I'm not jumping into the, I didn't multiply by root 15 over root 15. I could have. I would have gotten a root 75, and I would have to simplify that. A lot would have had to have been involved. And like I said, I don't want to linger. I'm already 10 minutes in. So, I'm on the part that's not even about the similarity in right triangles. So I hope this helped you, though. All right. So like I said, this did get here. Let's do the, I said similarity in right triangles. I meant special right triangles. Here are the special right triangles, 45, 45, 90, and 30, 60, 90. Let's see what this is all about. This is why you're here. These two are why you're here. Okay, the 45, 45, 90 right triangle is a right triangle with two 45-degree angles, and obviously a 90-degree angle, right? That's what it means. Now, here's what's special about it. The side lengths of a 45, 45, 90 triangle have a special ratio relationship of what's called 1 to 1 to root 2. You're going to hear me say 1 to 1 to root 2 a lot, where the hypotenuse is root 2 times larger than either of the equal legs. What does all that mean? Let's get into it right now with a proof of it. First of all, a 45, 45, 90 triangle is also an isosceles right triangle because base angles here are congruent, where you have a vertex angle of 90. Base angles are congruent. If it's isosceles, that means these sides opposite those base angles are also congruent. So let's say, we don't know what these side lengths are yet, right? So let's give one of these legs x. I don't know what it is, but I'll call it x. If this is x, that means this is x right here. It has to be. They're isosceles, right? They're the same. How long is this one? How long is this one? Let's call it c for a moment, but I want the value in terms of x here in a moment, right? Let's use Pythagorean theorem. Let's find out how long c is in terms of x. So let's solve for c. A squared plus b squared equals c squared, right? If I combine like terms, I'm going to get 2x squared equals c squared. Let me rewrite it so c squared is on this side because I want to make it say c equals. Let's take the square root of both sides right here. And we're going to get c equals, there's not going to be a plus or minus because it's a distance. So just like you saw me split before, guys, I'm going to split this up right here. Root 2 times root x squared. And the square root of x squared is x, just like the square root of c squared is c. So I'm going to write that as x root 2. This isn't necessarily something you have to know. This is just kind of me giving you an indicator of kind of how it can be shown and really what the ratio means in and of itself. So c can be rewritten as x root 2, guys. Here's what we have. What does all this mean? And by the way, this is true for every 45, 45, 90 triangle. What does this mean? It means that if you knew a leg length in your 45, 45, 90 triangle, if it was some x that you knew, maybe it was 7, who cares? But if you knew what it was, you can find the hypotenuse simply by multiplying this length by the square root of 2. And if you knew the hypotenuse value, whether or not it had a root 2 in it, this isn't about it having a root 2. It's about being root 2 times larger than this number. If you knew the hypotenuse, you could find either leg length by taking the hypotenuse length and dividing by root 2. And by the way, guys, these two are equal to each other right here. So if I want to find the other length, it's equal to it. So I just rewrite whatever the other one is. So this is what we're going to do here. Now, why do we say 1 to 1 to root 2? Because if one of the leg lengths was 1, then the other is 1, and the hypotenuse is root 2. That's all it means, because it's root 2 times larger, right? 1 times root 2 is root 2. Root 2 divided by root 2 is 1, and 1 equals 1. So let's do some examples right here. And by the way, we might have to simplify some radicals, either by rationalizing denominator or pulling out perfect squares, things like that. We might. We'll see. Okay, let's find x and y in this here right triangle that has a 45-degree angle. Well, I guess that means this one's 45 because that's just how they are, right? These two have to add to 90, or all these have to add to 180. So it's a 45, 45, 90. Awesome. That's good for us to know. And it's good because we know this is isosceles. You know how long y is? It is 8 root 2. Know how I know? Because the legs of an isosceles right triangle are congruent. I have solved for y. Sometimes you can, rewrite this if it does help you. And listen, guys, I can use Pythagorean theorem to find x, but the point is there are faster means. And it says such. X is going to be taking one of these leg lengths and multiplying it by the square root of 2. So we're going to take the leg length of 8 root 2, and we're going to multiply it by the square root of 2, and that's going to give us the value for x. We've seen a couple of these with just the simplifying radicals, right? Root 2 times root 2, guys, is 2. So I'm going to take 8 and multiply it by 2. And that's 16. So y is 8 root 2, and x is 16 right there. And that is that length. So that one cleaned up a little bit better as far as not having any irrational value. That's great. So that's what we did. We multiplied by root 2 there. All right, now what if you have a hypotenuse value of 2 in a 45, 45, 90 triangle? Let's find one of these values. How about we find y first? But of course, it's not going to matter. Once you find one, the other's the same. The hypotenuse is root 2 times larger, so I'm going to divide by root 2 this time to get the value of y. So y is going to be 2 divided by root 2. And that could be your answer, but as you saw from simplifying radicals, we must rationalize the denominator. So I'm going to multiply top and bottom, root 2 over root 2, and I'm going to get 2 root 2 over 2, which is just the square root of 2. That is the value of y. And guess what? X is equal to y. If y is root 2, x is also root 2. So yes, this is how, sorry if that's kind of in the way, this is how 45, 45, 90 triangles work here. The hypotenuse is always root 2 times larger than either leg, which are equal to one another. There are a lot of different examples you can do, especially with the simplifying radicals. It can get confusing and jarring, all depending on what's provided. I hope I gave something that's a little unique and special. I'm not giving you the super easiest ones, because hopefully you can do the super easiest ones. All right, that's the 45, 45, 90 triangle. That is that one there, and like I said, I could do more, but I'm going to dive into 30, 60, 90 right triangle, which it might be a little more complex, but let's take a look at it. So the 30, 60, 90 right triangle is a right triangle with a 30-degree angle and a 60-degree angle, of course, with its 90. The side lengths have another special ratio relationship. By the way, only the 45, 45, 90, and 30, 60, 90 have these clean-looking ratios like this. Anything else is so finicky that we got to use trig. And if you haven't learned trig yet, I haven't taught it to my students either, so we'll get there. That's what's coming next. Not in this video. So here's the special ratio relationship of a 30, 60, 90. It is 1 to 2 to root 3. The hypotenuse is twice as large as the shortest leg. The shortest leg is opposite the 30-degree angle. We'll get into all that with the proof. You'll see it. And the longer leg is root 3 times larger than the shortest leg. I kind of didn't really get this. Root 3 times larger than the shortest leg. So everything really you want to compare to the shortest leg. Okay. Now, let's get a proof of this one. It's going to be a little finicky. It's going to be a little weird. And you don't have to go with me in full. It's me kind of convincing myself. Okay. If you saw last time, guys, I assigned x to one of the legs, to the 45. Now, both of them were x here. It kind of makes most sense to do it opposite the shortest leg, so everything that's larger I can just multiply. So opposite the 30 is the shortest side. I'm going to give this x, okay? Here's what I'm going to do next. I'm going to reflect this triangle and merge it together like so. Why are you doing this, Mr. Robinson? Because what I've just made, if this is 60, this is 60, right? And if this is 30, this is 30, which means the whole thing is 60. What I just made was an equiangular triangle. And you know what's true about an equiangular triangle? It's also equilateral. An equilateral triangle means this is congruent to this is congruent to this, meaning the entire side right here. Why is this all important? Because if this is x, this is also x, right? This was just a reflection. You know what that means this whole side is? This whole side is 2x, which means this whole side is 2x, and this is what I wanted to show you. This is 2x. This is 2x right here. The hypotenuse of my 30, 60, 90 is 2x, Hey, I don't need this anymore. I'm going to get rid of this. I just wanted to show you that that was 2x. That's all I wanted to do that for. That's a proof of that being 2x. Creating an equilateral triangle within by reflecting and then having congruent parts x, x, and 2x. Great. Okay, so that's 2x. Well, what about this length right here? Let's call it b for a moment. Let's use Pythagorean theorem again. A squared plus b squared equals c squared. And I want to solve for b. Well, let's go ahead and expand 2x quantity. What did I just do? Let's expand 2x quantity squared into 4x squared. Let's subtract x squared from both sides, and let's take the square root of both sides here. We're going to get b squared equals x times the square root of 3. Again, the square root of x squared is x, and then the square root of 3 is that. So x times the square root of 3. What does that mean? It means that whatever the side opposite 30 is, the side opposite 60 is going to be root 3 times larger. And of course, the hypotenuse, like I said, was twice as long, 2 times larger. So if I knew the side opposite the 30, and I keep saying opposite the 30 like this is what I mean, the shortest side. If I knew the side opposite the 30-degree angle, I could find the hypotenuse by multiplying this length by 2. And I could find the angle, the side, opposite the 60-degree angle by multiplying by root 3. If I knew the hypotenuse, I could find the side opposite the 30-degree angle, the shortest side, by dividing by 2. And if I knew the side opposite the 60-degree angle, I could find the shortest side opposite the 30 by dividing by root 3. There is no really one nice clean way to go from the side opposite 60 to the hypotenuse. It's best to just work your way around like that. Go to the shortest side, then go to the hypotenuse, just divide by root 3, get your number, then multiply by 2. And that's what I would do there. All right, so why does it say 1 to 2 to root 3? Because if you had a 30, 60, 90 triangle as follows, this is 30, this is 60. If the side opposite 30 was 1, the hypotenuse would be 2, and and this would be root 3 right here, the side opposite 60. Now, this one's a little different because, when you say 1 to 2 to root 3, sorry, let me back up one sec. On the 45, 45, 90, when I said 1 to 1 to root 2, these also lined up with each other. The side opposite 45 is 1, side opposite 45 is 1, side opposite 90 is root 2. Although in the 30, 60, 90, it's a little, it's not quite here. The 1 is with the 30, but when I say 2 and root 3, well, the root 3 is associated with the 60, right? And then the 90 is associated there. So this is more of a, when you say 1 to 2 to root 3, it's just more of a memorization tactic. 1, 2, 3, right? It sounds easy to kind of remember that way. But, 2 is larger than the square root of 3. And I hope you know that because the square root of 4 is 2. So the square root of 3 has to be less. So, the square root of 3 is assigned to the opposite 60 there. You're just going to have to know that when I say 1 to 2 to root 3 in a 30, 60, 90, the 2 is really for the opposite 90, right? It's the bigger one there. Anyway, I just wanted to let you know that when I say that, it's better than saying 1 to root 3 to 2. That doesn't roll off the tongue. It doesn't roll off the tongue. All right, let's go and do some examples, guys. Here we go. I have 36 opposite the 60. This must mean this is 30, right? I need to find out B and A. Like I said, there's no fast way to go to the hypotenuse from here, at least not a clean way. Not that this could be the cleanest of all problems here. But if this is like the root 3, if this is root 3 times larger than this guy right here, I'm going to have to divide 36 by the square root of 3 to figure out B. Okay, so B, I'm going to take 36 and divide by root 3. Hey, I got to rationalize the denominator. So I'm going to multiply top and bottom by root 3. And that's going to get me 36 root 3 over 3. And 36 over 3 is 12. So B, guys, will be 12 root 3. That is the length. And, I think you can appreciate the simplification there. No more fraction. There's my number. A is going to be taking the side opposite the 30, the 12 root 3, and I'm going to double it. So A is 12 root 3 times 2. And only the 12 multiplies with 2. It's not like it's a distribution and rational multiplies with rational. So A will be 24 root 3. That is my value for for A. And again, I'm saving myself from using Pythagorean theorem in this case. And there's a special relationship. There it is, in the actual value. All right, let's go ahead and solve for y and x here. I do have the side opposite the 30. That means this is the shortest side of my set. Here's the 60 degree. Let's do the hypotenuse first. I think it's just going to be a faster, quicker value. I just got to multiply this by 2, right? The hypotenuse is twice as long. So x is going to be 4 root 3 doubled times 2. That's going to be 8 root 3. Now, I'm not going to use my 8 root 3 to help me find this one here because it's faster to go from the 30 degree angle to the 60. From 30 to 60, what do? We got to multiply by the square root of 3 here. So y is 4 root 3 times root 3. Well, root 3 times root 3 is 3, so it's 4 times 3. Y is 12. Hey, that cleaned up for me right there. So x is 8 root 3. Y is 12. We have found our values. And let this right now be an understanding in a lesson. This is well before we do any trig, guys. Let this right now be an understanding in a lesson that just because an angle is twice as large doesn't mean the side opposite is twice as large, right? The opposite, 60 is twice as large as 30, but the side opposite 60 wasn't twice as large. It's root 3 times larger. So the ratio relationships don't grow in proportion the same way that the angles do. If they did, there would be a lot of things that would be broken with math if it worked like that. So just keep that in mind. It's not like that. All right, that's probably what you were most here for, guys. So that's the 45, 45, 90, and 30, 60, 90. I'm going to end on Pythagorean triples. I'm going to be very fast with this. This isn't something that's required, but something that saves you on Pythagorean theorem in a lot of common integer right triangles here. And here's what this says. Oh, I wanted to change the color in the back, but that's okay. Okay, guys, a Pythagorean triple consists of 3 positive integers a, b, and c such that a squared plus b squared equals c squared. What this means, guys, is there are right triangles that have integers only. You didn't see any in the 45, 45, 90s because there are some that are root 2 times larger, root 3 times larger. But there are some where you thankfully get all integer values. Now, there are some common Pythagorean triples that you'll see in right triangles, such as the 3, 4, 5 right triangle. What this means, I'm just going to draw one really fast. What this means is in a right triangle, the shortest leg being 3, the longer leg being 4, and the hypotenuse being 5. A 3, 4, 5 right triangle, 3 squared. So what this means, guys, is 3 squared plus 4 squared is 5 squared. I'm just letting you know right now. 9 plus 16 is 25. Yes, that's true. 3, 4, 5 is a special right triangle. It's not like there's a 2, 3, 4 right triangle because 2 squared plus 3 squared doesn't equal 4 squared. So when I'm saying these things, that's what this means. The longest side being the hypotenuse. 3, 4, 5 is a common Pythagorean triple. 5, 12, 13 is 1. 8, 15, 17 is 1. And 7, 24, 25 is 1. These are the 4 smallest ones with regards to being unique. And I'll let you know what that means in the next sentence. But these are the 4 smallest unique ones. I actually don't know any larger unique ones after this off the top of my head. But this list does continue infinitely. Sorry, 1 second. I have a little sniffle thing. I'm going to pause for 1 quick second. That was legit a quick sec. I just didn't want a sound effect. All right. Upscaled iterations. I'll let you know what that means. Upscaled iterations of Pythagorean triples also qualify. When you see a 6, 8, 10, that's really just another version of 3, 4, 5. How come? Because the values of 3, 4, 5 are doubled. So it's, that's triangle similarity. When you double everything, the triangles are still similar by angle. The similarity ratio is 2 to 1. So, I can double my values and it's still a 3, 4, 5. It's a version of a 3, 4, 5. So that's why when I said these are unique, 6, 8, 10 may be less than 8, 15, 17, but it's just another version of 3, 4, 5. So let's take a look at some of these. Let's find out some of the missing side lengths. The first one here, 8, an unknown, and 17. Well, if you know these, then that's 8, 15, 17. So there's the unknown. That was an easy one. And that's the thing. That's the point. If you see some of these guys, if you see them enough, you'll kind of just know. You're like, hey, I know what that is. Some of these other ones, hey, we didn't look at one that had 10, 24, and blank. But remember, guys, these triangles are similar to smaller versions of these triangles. If I divided 10 by 2, I'd get 5. If I divided 24 by 2, I'd get 12. So this is a 5, 12, 13. This side would be 13 if these were divided by 2, right? This is a 5, 12, 13 in that kind of way. Well, what would have the original been? 5, 12, 13, 10, 24. You got to double 13. You get 26. That's what that length is right there. So hopefully that makes sense. Everything's twice as large as 5, 12, 13. And then we do that. So if you can recognize what it is, then you're in good shape. 60, 80 blank. Well, we've seen the 6, 8, 10 be a version of a 3, 4, 5, right? So 60, 80, 10D, 60, 80, 100 could be that one. Hopefully, and if this isn't making sense, that's okay. You can always use Pythagorean theorem, but this is just another version of 3, 4, 5, where everything is 20 times larger. It's a 20 times larger version of 3, 4, 5. Blank 24 root 3, 25 root 3. Well, you've seen 7, 24, 25. I'm guessing this is 7 root 3. Everything is root 3 times larger there. And yes, when I'm saying I'm guessing, I mean it is true. And the last one here, what if I divided all these by 5? I'm saying by 5 because they can. 65 divided by 5 is 13. This must be the 12 version of it. So if I multiply 12 by 5, right, then this would be 60. So that's just to clean that up. So that's 60 right there. That's the missing length. Again, just saving myself Pythagorean theorem. Pythagorean triples do exist. They are there. And the more that you see them, the more they'll help you. Anyway, because you might hear me say things like 3, 4, 5 and stuff down the line. I don't know if I will because we're going to run into some trig later. So we'll see. But that'll be it, guys. That was the last thing there. You were probably here for these two. I hope that you learned something, a thing or two there. And yeah, thank you so much for watching, guys. This is Mr. Robinson. I'll be back with you next time, I believe, with some trig stuff. So be ready for that. Take care.